Hello, guys, and welcome back to Med Zone African Motives. Like I promised, I said that in this video, we are going to be looking into the principle of conservation of linear momentum. So, there is a law that governs our conservation of linear momentum. That law is the one that we use whenever we are solving problems to do with what? With conservation of linear momentum. So we are always going to be given either collisions or anything to do with collisions, and we apply this principle. And the principle of conservation of linear momentum, it states that the total momentum of an isolated system remains constant provided no net external force acts on the system. So what is it that we mean? We are saying that total linear momentum before collision should be equal to total linear momentum after collision, or else the total linear momentum before anything happens to our objects should be equal to after an action that would have occurred. So we are saying that, let's say I have got object 1, object 2, object 3. I would say momentum of object 1 plus momentum of object 2 plus momentum of object 3 before collision should be equal to what? Momentum of object 1 plus momentum of object 2 plus momentum of object 3 after collision. That is to say that the mass of object 1 and velocity of object 1 plus mass of object 2, velocity of object 2, plus mass of object 3, velocity of object 3. That is initial, or else before initial, should be equal to what? Mass of object 1, velocity of object 1, mass of object 2, velocity of object 2, plus mass of object 3, velocity of object 3, after, or else final. That is what we call the principle of what? Of conservation of linear momentum. Once we know that, we will have many different types of, or else let me say that we would have four different types of scenarios, which relates to our different types of what? Of problem types. And in those different types of our problems, we are going to use different methods in terms of what? Of solving them. But they will all fall under the principle of what? Of conservation of linear momentum. So before we get to look into those problems, I want us to look into the steps that we are going to be using in solving our problems in regards to conservation of linear momentum. So the first step to do is to choose a direction that you term positive. Like, for example, if you get to say that let going to the right be positive, then you should maintain going to the right to be positive. So any car or else any object that would be going towards the left will have a negative velocity. So the velocity is the one that would be having direction. Since we know that momentum is given by mass times velocity, so the direction of the velocity of each object should be in accordance to the positive direction that you would have chosen. So always start by choosing your positive direction, and then be consistent, or else take that direction to be the direction that you are going to use as you go up until you finish that problem. After that, sketch the situation, that is to say, draw a block for each object, or else draw a block to represent each object. If they say there is a trolley that is moving towards the right, this should be your trolley. So sketch it so that we see that this is trolley A and it is going towards the right. If they say it is colliding with another trolley that is going towards the left, then let this be trolley B, so that we get to have an idea, or else you actually get a picture of what they are saying, so that it becomes easier in actually solving the problems. So the first thing to do is to choose a positive direction. That is to say, if I say going towards the right is positive, I will take that direction to be positive. And then I sketch or draw a block to represent each object. And then thereafter, I need to now get to expand my scenario into initial and after, or else initial and final. And then I write down the equation for the conservation of momentum. That is to say, once I know that this is my initial scenario and then this is my final, or else let's say this is before and this is after collision, I will now come and say total linear momentum before should be equal to total linear momentum after. And then thereafter, I will now get to expand everything into this equation. That is to substitute the known values into the equation. Where I know mass 1 V1 and where I know mass 2 V2, before I'll substitute those values. That is what we mean. So these are the steps that we are going to be following. And then thereafter, you can calculate the answer and then write the answer, including correct units and indicating the direction of your answer. So let's get started with our different problem types. So the first problem type that you are going to be given, or else that we are going to meet in our exams, in our test, in our exercises, is when we have got two objects that collide, and then after colliding, they move separately. Like for example, let's say initially I've got trolley A that is moving towards the right, and then I've got trolley B that is moving towards the left. These two trolleys, they collide. That is before. And then after collision, these two trolleys, they will now get to what? They will now get to separate. The other goes its own direction and the other goes its own direction. Meaning to say that maybe this one will go this direction as well as this one will go this direction, but you would be having trolley A and B separated. They collide and then they separate. But when they separate, they are now going in the same direction. Or else, when they separate, we'll get to see that it might be A who is going continuously going in that direction, and it might be B who will continuously go in that direction. Or else, you would see that instead of A going in that direction, we would have A go in this direction now, in the opposite direction to which it was moving, and also B going in that opposite direction. But what we would have is two objects colliding and then they get to separate. So let's get to see this example that is in regard to that. We are told that two objects of masses 2 kg and 3 kg move towards each other with velocities 4 meters and negative 2 meters. So let me say that the first object has got a velocity of what? 4 meters per second. And this object has got a mass of 2 kgs. And then I have got another object that has got a mass of 4 kg that is having a velocity of negative 2 meters per second. So now, since I have already indicated that the one that is having a positive direction is going towards the right, therefore this one that is having a negative velocity will go towards the left. And they are saying that these two objects, they collide. So that is before. That is the scenario before. After collision, the 2 kg object moves at negative 1 meters per second. So the 2 kg object, this is my 2 kg object, it's now moving in the opposite direction to where it was moving, because now it is moving at 1 meters per second. So that is in the negative direction. And then we do not know what happens to the 4 kg block. Either it is going to go in that direction or else in that direction. And how much will that, sorry, here I'm using 4 kg. This is 3 kg. So we need to find the final velocity. Definitely would be asked. They are now saying calculate the final velocity of the what? Of the 3 kg block. So how do we do this? This is where now I now know my scenario before and after, and I've chosen my positive direction to be towards the right. This is positive. And then I get to apply the principle of conservation of momentum. I get to apply the principle of conservation of what? Of momentum. Where I would say that momentum, total momentum before should be equal to total momentum after. Therefore, what is my momentum before? That is momentum of what? Of this 2 kg block plus momentum of the 3 kg block being equal to momentum of 2 kg block plus momentum of 3 kg block. But this is before and this is after. And then I would come now and substitute the values that I know. That is to say, mass of object 1 and velocity of object 1, mass of object 2 and velocity of object 2, before equal to mass of object 1, velocity of object 1, mass of object 2, velocity of object 2, after. And then what is the mass of object 1? That is 2 kgs. And what is the velocity of object 1? That is 4 meters per second. Plus, what is mass of object 2? 3 kg times a velocity of what? Negative 2. We were given a velocity of what here? We were given a velocity of negative 2 because it's going in the negative direction. And then after, we've got a velocity of negative 1 for this one, and this one we do not know the velocity. So we just come and fill in the knowns and we leave the unknowns. So now we know that 2 times negative 1, but we do not know the velocity of this one. So we say final velocity there. This is what we are looking for. So we can go further to say 2 times 4 becomes 8 plus 3 times negative 2, it becomes negative 6, equal to 2 times negative 1, it becomes negative 2, plus 3 times VF, it becomes 3 VF. I will transpose this to the other side. And then 8 minus 6, I will say 8 minus 6. And then this one becomes a positive when it comes this side, plus 2, is equal to 3 VF. 8 minus 6, it's 2. 2 plus 2, it becomes 4. So 4 is equals to 3 VF. And then I divide by 3, I divide by 3. So my final velocity here, you would see that my final velocity here, it will cancel out. I'll be left with my final velocity being equal to 4 over 3. So you can see that is positive meters per second. So I will simply say that my final velocity is in the opposite direction in which this object was moving. So if I just leave it as positive 4 over 3 meters per second, it is already indicating the what? The direction. So remember to indicate direction. So that is our first scenario. Now let's look at our second scenario. Let's look at our second scenario. This is when now you have got two objects colliding, and then after those objects collide, they will now get to unite. What do we mean by that? We have our object A, let's say going towards the right, and object B going towards the left. They collide these two, and then after collision, we have got object A and object B becoming one thing, and they'll move with the same velocity. So here mass of A, we will sum it with mass of B. but the velocity will be the same. But this side, I will be having mass of A times velocity of A plus mass of B times velocity of B initial. So this would be initial, and this would be after, or else final. It's just the same thing. So this is what we mean by two objects colliding and then uniting. So how do we get to solve this? I've already indicated how we can structure them. So let's look at this given example, and then let's apply what I've said. A 1 kg trolley moving at 6 meters per second collides with a stationary 2 kg trolley. So we are saying that I have got a trolley which is 1 kg. I've got a trolley that is moving at 6 meters per second. So I've already determined my positive direction to be towards the right. And then I have another trolley, which is 2 kgs, that is moving at what? Collides with the 2 kg trolley. It's not given its velocity there. And then they say that. So here I can see that we are not, it's me who is actually, they say that the 2 kg trolley is stationary. Let's take note of that. So the 2 kg trolley, this is my 2 kg trolley with its wheels, but it is stationary. So its velocity, the velocity of the object 2, it's 0. And then they're saying after collision, these two trolleys, they stick together. Trolley of 1 kg and trolley of 2 kgs, they stick together. When they stick together, we now want to find what becomes the what? The final velocity. We do not know if it is going to go to the right or to the left, or else it will remain stationary. We want to find that what? That final velocity. So this is where we said we now come and apply the principle of what? Conservation of linear momentum, where we are saying that total linear momentum before, I will represent it with initial, should be equal to total linear momentum final. So what is my total linear momentum before? That is the mass of the 1 kg block times its velocity there, plus the mass of the 2 kg block times its velocity there. Then before should be equal to mass of object 1 times mass of object 2 times the final velocity. So what is the mass of my 1 kg block? It's just 1 times what is the velocity? 6 meters per second. Plus what is the mass here? It's 2 kgs times what is the velocity? 0. So I will add these ones, and then I would equate to what is my mass here? 1 plus 2 times final velocity. Then I can be able to what? To calculate that final velocity. So here what I'm going to do, I'll just come and say 1 times 6, that is 6, plus 2 times 0, that is 0. So this one will be like this. 1 plus 2, that is 3 times my final velocity. And then I'll divide by 3, I'll divide by 3. This side I would get 2 meters per second, which is just a positive. And then these ones will cancel out. And then my final velocity of these two objects will be 2 meters towards the right, 2 meters per second towards the right. So that is how we solve our what? Our second scenario. That is how we solve our second scenario. So this is what we have done. These two objects, they collide whilst this was stationary, and then they start moving together, and then this is how we find the final velocity. Now let's look at our third scenario. Now they're telling us that we might have an explosion which is starting from rest. So we are saying, let's say that at some point in time, I would be having a rocket. I'm trying by all means to draw a simple depiction of a rocket. Let's say that I'll be having a what? A rocket. So this becomes my what? My rocket. And then that being my rocket, you know that I would be having, this is the fuel of my rocket. But however, for now we are saying that our rocket is stationary. So this is our rocket before launch. This is our rocket before launch. This example is the perfect example that can help us to picture this scenario where we are saying that we can have an explosion that is coming after what? From rest. So we are having our rocket before launch, and then we will now have our rocket after launch. So now we are now saying that this becomes our rocket after launch. Just pardon my drawing there. I'm just trying to give a depiction of a rocket. So let's say this now becomes my rocket after launch. This is my rocket after launch. So now my rocket is having a certain what? Velocity that is going upwards. So this is what we refer to as an explosion. So for those who know and understand how a rocket launches, a rocket has got its fuel. So that fuel is the one that is ignited. Once it's ignited, it explodes. When the fuel explodes, our rocket launches. So that fuel explosion is the one that gives our what? Our rocket the initial velocity. So this is the what? The scenario that they might actually guess to what? To refer to. So now let's hear what they are saying in this example. I'll keep this diagram because I don't want to repeat this drawing. Two objects initially at rest stick together. So we have got two objects that are initially at rest. During an explosion, they move apart. If one object is mass 2 kg and velocity of 3 meters per second, calculate the velocity of the other object with mass 1 kg. So maybe let's get to say that this becomes my fuel. Let's say this is my fuel bag. So that is the first object. That becomes my fuel bag. I'm just giving an example because I don't want to repeat this drawing. It will kill our time. And then this becomes my rocket. And then this rocket, they are saying that it is having a mass of what? Of 2 kgs. And then this one is having a mass of what? A mass of 1 kg. And then they are saying that initially they are stationary, as I have said. So their velocity is equal to 0. That is, their initial velocity is equal to 0. But after launch, this rocket is now having, so let me say, velocity of rocket is equal to what? 3 meters per second. So let's take upwards being positive. That becomes 3 meters per second. That is the velocity of the rocket. What becomes the velocity of the bag? That is what they are asking now. Now, this is where we now come and apply our linear momentum what? Theorem, where we will now get to say that total linear momentum before should be equal to total linear momentum after. And then I get to say that mass of object 1 plus mass of object 2, because they stick together and then they have got an initial velocity. And then after collision, they get to separate. Then mass of 1 and then velocity of 1 plus mass of 2, velocity of 2, final. So mass of 1, it's what? It's 2 kgs plus 1 kgs times initial velocity, it's z, equal to mass of 1 mass of 1 is 2 kgs times the initial velocity is 3 meters per second plus mass 1 kg times the final velocity that I do not know. Now I want to find this final velocity. So this would actually be equal to 0 because anything multiplied by 0 is 0. And then 2 times 3, that's 6, plus 1 times 1 times Vf, that becomes final velocity. So this is the final velocity, let's say, of the bag. Now I will transpose this, that other side, it becomes negative 6. And then this one becomes what? Vf bag. So the final velocity of my bag would simply be equal to what? Negative 6 meters per second, which actually does make sense in such a scenario that if the explosion will cause this rocket to go up, if it will cause the rocket to move up, then its fuel bag would actually be pushed down. So let's get to say this would be the fuel bag. So I'm sure you would actually get to see that when there is this explosion, that smoke or fire of the fuel, it is actually directed downwards. That's why you would see your smoke or else your flame going downwards. So it will make sense to say it would be negative 6 meters per what? Per second there. So that is our third scenario. Let's look at our fourth and final scenario here. So our fourth and final scenario says object falls onto a moving object. You would be having a trolley that is initially moving in that direction, and then there is an object that would be thrown to that trolley. And then at some point in time after, you would find that object inside the trolley and they'll be moving together. That is the scenario. So you would see that since our scenarios, or else let's get to say, whenever we are dealing with change in momentum, we are always going to look into what? Into linear momentum. Linear momentum means that momentum in the same plane. So we cannot be able to look into what? Into vertical direction as well as horizontal direction. So if we consider to be looking into the momentum of the what? Of the horizontal direction, then it means that whatsoever is moving vertically has got a velocity equal to 0. I want you to understand that. If we are going to be looking into linear momentum along the horizontal direction, anything that is moving along the vertical direction has got a horizontal direction, has got a horizontal velocity equal to 0. So anything that is moving down or up would be regarded as having a velocity of 0 because we are dealing with the horizontal momentum. But if we choose to deal with the vertical momentum, anything moving in the horizontal direction will also have a velocity of 0. So we need to decide which scenario are we looking at. So we are always going to be looking into horizontal linear momentum whenever we have got two objects, either the other one going down and the other one going horizontal. So we are always going to take this one, so that the one that is moving vertically would be having a velocity of 0. So now they are saying a 2 kg object moving at 5 meters per second horizontally is a 1 kg object dropped onto it from above. So we have got this 5 kg object moving with a velocity of what? 5 meters per second. So I've taken going to the right to be my positive direction. And then I've got an object that is 1 kg being dropped. So the initial velocity, so let's say this is object A and this is object B. So the initial velocity of object B will be equal to 0. After collision, they move together. So after collision, I now have the object there inside that is A and B. So I now have object A and object B. Now they are now moving together, but we do not know the final velocity. Now they say calculate their final velocity. So we also apply the principle of conservation of linear momentum, and then we say total linear momentum before should be equal to total linear momentum after, which says to say total linear momentum of object A, which is given by mass of A times mass of velocity of A plus mass of B times velocity of B, initially should be equal to mass of A plus mass of B times final velocity. Because they are going to move together, these ones. So they will be having the same final velocity. They will be having the same final velocity. After I've done that, I will now come and substitute the values that I know. Mass of A is 5 kg times the velocity of A, it's a positive 5 also, plus mass of B, it's 1 kg times initial velocity of B, it's 0. Why have I said that it's 0? Because object B is going down and we are looking into the horizontal motion. So this one would actually result to be equal to what? To 0. So the velocity of B is 0. And then thereafter, mass of A is 5 plus 1, and then times the final velocity. That is what I'm looking for. Now, 5 times 5, that's 25. Plus anything multiplied by 0 is 0, equal to 5 plus 1, that's 6, times VF. I divide by 6, I divide by 6. And then I know that these ones will cancel out. I'll be left with final velocity of both objects. That will be 25 over 6 meters per second. So you can see that it is positive. So this object will continue moving towards the right. So those are the 4 scenarios, or else those are the 4 problem types that we are always going to meet in our conservation of what? Of linear momentum. And that is how we attempt them, or else that is how we get to calculate whatsoever missing is there. So thank you guys. Let's meet in our next videos when we are now going to actually get to look into what? Into collisions. That's when we are now looking into elastic and inelastic collisions.